Welcome to the 0th Affliction Devlog. In this video, I'll discuss the project's background and objectives, and then cover the principles and goals that'll guide the development of this epidemiological simulator. Stick around, I'll show a preliminary design for the Affliction heads-up display as I begin planning out the graphical user interface. Epidemiology is a field of science focused on studying and analyzing the distribution, patterns, and determinants of health and disease conditions in populations. To explore this vast discipline, I'm in the early stages of ideating and developing Affliction, an epidemiological simulator built on the Tartarus game engine. Affliction aims to combine the principles of game development with those of computational epidemiology to provide an interesting and engaging way to investigate various epidemiological concepts and scenarios. As you've probably already guessed, the idea for Affliction was born out of recent and even ongoing events. Every viewer is probably keenly aware of an epidemiological cataclysm that's unfolded since late 2019, known as the COVID-19 pandemic. Life in early 2023 is largely back to normal for many, if not most people, but the pandemic wreaked havoc across the globe, especially throughout the first year or two. Many experienced financial distress, hardships in mental or physical health, or even the loss of loved ones. Although Affliction and this accompanying devlog series are intended to explore epidemiology in a fun, engaging, and lighthearted manner, it's important to remember that real people just like you and me, have suffered. To all who were deeply affected during the last few years, perhaps you or your loved ones, I extend my condolences and compassion. I'd also like to explicitly state that Affliction is in no way a political, philosophical, economic, theological, or societal commentary. I'm just some dude who likes video games and programming and thought epidemiological simulations would be dope. And since division is so pervasive on the internet and across the globe, I'll say up front, whatever your convictions are regarding the COVID-19 pandemic, kindly reserve those thoughts and opinions for meaningful in-person conversations you can have with loved ones, your community, and your local leaders. So, what gave me the idea to start a project like this? Well, one of the videos I watched near the middle of 2020 explored the spread of viruses using simulations. I've included a link to the video in the description, and I strongly encourage you to watch it. That video stoked my curiosity and imagination, leading me to wonder how I might create a similar simulation with more opportunity for customization. As gears turned and plans solidified, the idea of creating a three-dimensional epidemiological simulator was born as Affliction. Without getting into the specifics so as not to spoil these ideas, I'm really interested in doing some epidemiological simulations. Funny enough, I was working toward Affliction before the first engine devlog was released, and even before starting this YouTube channel. Now that we've established the motivation behind the project, let's talk about what I'm aiming to achieve with Affliction. I've listed a few high-level project goals here that'll guide the theme of my work. Obviously, my primary goal is to develop a working simulator, but the second objective expands upon this. As I mentioned just a few moments ago, Affliction is built on the Tartarus game engine. Arguably, Tartarus's most important feature is that it's built with an Entity Component System Architecture, or ECS. As I'll describe more in a little while, ECS makes it exceptionally easy to add new features, rules, and interactions to a game or simulation. I'm hopeful that ECS will allow emergent phenomena to arise, that adding just a few layers of complexity will produce unexpected, if not surprising, results. Third, I want to be able to interact with the simulated world, to start, stop, and reverse time, add or remove creatures, and so on. Eventually, I also want to be able to serialize and export the data so that I can perform deeper analysis like regression using Python. And lastly, the most nebulous project goal is to find some sort of result. What result, you might ask? I don't know yet, but I'm eager to see whether accomplishing the previous four goals will lead to some kind of interesting observation or conclusion about the simulated world I've created. Summarizing this slide, my objective is to simulate an environment populated by interacting creatures that can contract and transmit diseases, study these creatures and processes over time, and glean whatever insights might be available. That kinda sounds like research, but that leads me to my next and likely most critical point. The simulations I'll eventually perform will not constitute peer-reviewed scientific research or medical advice. Rather, they're simply meant to demonstrate approximations of real-world processes much like any other video game. Eventually, when I release videos that show actual simulations, you'll probably see a disclaimer at the beginning of each to remind viewers that I'm just some guy that thought it'd be cool to explore epidemiology as a side project. I'm neither a physician nor an epidemiologist, but I am an expert at unintentionally introducing bugs into code. Except after I implemented this, I ran face first into a nasty bug with a picking system. You shouldn't trust anything I say regarding epidemiology because, generally speaking, I have no idea what I'm doing, and I'll smile while unintentionally driving us both over a cliff. Now, before getting into Affliction's composition, I'd like to revisit a topic I've mentioned a few times already and covered in more detail in Engine Devlog 1, the Entity Component System Architecture, or again, ECS. I'd encourage you to watch that video if you'd like a bit more discussion of the fundamentals, but for now, I'll repackage some of those ideas in a slightly more intuitive and tangible series of analogies for those of you less interested in the gory details of engine development. This will provide us with the machinery to better understand the key ingredients of an Affliction simulation. Let's suppose you're in the very early stages of game development for a unique, flexible racing game. More specifically, you're in the planning phase, trying to strategize different vehicle designs that players might want to race. Instead of drawing all these ideas by hand, an easier way for you to test design ideas is to arrange various magnets on your refrigerator door. So you purchase a few magnets, one of a sports car and another of a fire truck, as a starting point for your designs. But you quickly realize there's a limitation. These vehicle magnets aren't really customizable. You can't rearrange parts or try unique designs because you're stuck with a whole magnet of a sports car and a whole magnet of a fire truck. One day, you stumble upon Engine Devlog 1 and realize that ECS might be the solution to your problem. Instead of buying magnets of entire vehicles, what if you bought magnets of vehicle parts? That'd allow you to assemble things like vehicle bodies, wheels, and so forth without any constraints on how these different parts are arranged. Now, if you want to make a sports car, you just need to combine the sports car body and two wheels. If you want to make a fire truck, similar idea. Get the fire truck body, two wheels, a siren, and a ladder. You then realize that you have way more artistic freedom than before because with this new, more flexible design approach, you can easily make nearly any small or large change you want. You can trivially remove your fire truck's ladder or give it a third wheel. You could even get crazy and make a sports car with a fire ladder. With this approach, you have the ability to make whatever vehicle you want. In fact, as long as you have the right components, you don't even have to make vehicles at all. You could turn the fire truck body on its end and add a couple ladders to create a windmill, and give it wheels, and blazing sirens at the end of each blade, and whatever else your heart desires. As all these ideas surge into your head, you decide that your game will give players the same exact flexibility to create whatever vehicle in whatever style or arrangement of vehicle parts they can imagine. As you sit back and think about these vehicles and gameplay, you have another bright idea. What if different parts and configurations impacted vehicle performance, behavior, and ability? For example, it seems obvious that smaller, lighter vehicles should have a higher top speed, accelerate more quickly, and handle more precisely than larger, heavier vehicles. It would also make sense that bulkier vehicles would be more resilient to damage than their nimbler counterparts. But how would you implement these ideas in practice? Well, much like a wheel or a fire ladder, there's nothing stopping you from adding unseen properties to a vehicle, things like mass, health, armor, and so on. You design the game such that as players customize their vehicles, the mass, health, and armor update according to the vehicle's composition. Then, you implement various physical processes or functions in ways that depend on this variety of attributes. For example, you implement a vehicle acceleration process that's proportional to health but inversely proportional to mass, a health system that scales linearly with both mass and armor, and a collision damage system that depends quadratically on speed but inversely on armor. By adding these simple processes, you've created a very complex system of trade-offs in how users design their vehicles. For example, it's unclear which vehicle configuration is the most optimal and can likely only be determined with repeated gameplay. This approach of adding arbitrary properties to game objects and operating on those game objects with processes whose outputs depend on the value of the object properties is both powerful and flexible. It enables you to easily add new interactions to the gameplay. One day, you decide to add ramps to your game so that vehicles can launch into the air, so you create a gravitational force that scales with mass. You also want ramps to have limited uses, so you can give them health bars and create a process that applies a different type of damage to the ramp that scales with the mass and speed of the vehicle hitting it. You want air resistance, so you implement a force that depends on the cross-sectional area and squared speed of the vehicle. And on and on and on, until one day, you win the Nobel Peace Prize. Congratulations, I knew you could do it. Although this whole hypothetical scenario is a bit contrived, it portrays the principles of ECS rather nicely. Instead of defining entire objects in the video game, we define the pieces that comprise those objects. Then, we're free to assemble those pieces in whatever fashion we choose. The resulting entity is then just whatever Frankenstein of components we've aggregated. The systems in the video game are just processes that run on the entities that have the relevant components. The idea is that any game object can be given nearly any attribute, and any process can be implemented that defines how these different attributes and entities interact with and within the game world. Because these interactions are so non-linear and unknown to the developer, all kinds of unexpected and surprising things can happen. For instance, maybe it turns out that really small but heavily armored vehicles win the most races. Or maybe, just maybe, after implementing another process that allows the conversion of wind energy into electric propulsion, the windmill configuration from earlier turns out to be the best design. Who knows? And that's the idea behind ECS and emergent behavior, and that's what I intend to be the core of Affliction. Now that we're equipped with an understanding of entities, components, and systems, let's start digging into the crucial pieces of an epidemiological simulation. In principle, we just need 3 key ingredients: a game world or environment in which events can temporally and spatially transpire, a disease that can be contracted and transmitted, and a set of creatures or agents that can interact with one another, the disease, and the environment. How might we use ECS to implement all these? Well, let's step through each ingredient individually and then tie them all together. Entities will appear as blue circles, their components will be green boxes below with gray boxes defining the comprising properties, and systems will be represented as red boxes that point at the various components on which they either depend or operate. We'll hold off on defining the systems until we've covered the entities and components. Let's start with the environment, and let's consider real-world properties of an environment that might impact how a disease spreads throughout a population. We can surmise that something as simple as geographical size might impact the simulation. The more room creatures have to spread out, the less likely they are to transmit a disease, it would seem. So, to the environment entity, we add a geography component inside which we place a dimensions property that defines the map size. We could also suppose that the environment's temperature impacts how well the disease spreads, so we add a climate component that includes a temperature property. And so on. Next up, the disease. Diseases have many attributes that can impact when, where, and how they spread. We can add a profile component that includes properties such as disease transmission rate and infection duration. We might also wish to include a symptoms component that specifies how agents are impacted, perhaps with a fever or a cough. The disease might also impact other psychological or physiological behavior like heightened agility, aggression, and propensity to bite. A zombie virus, if you will. But one thing to consider is that there's no reason we're limited to just a single disease. We could have 2, 3, or any arbitrary number of them and implement each as its own entity. Each of these diseases can differ in the properties we've already described. Maybe diseases mutate, which introduces stochastic variations in some of the parameters. It's also possible for diseases to compete for the same host, or even for one disease to counteract the other. But one especially interesting thing to note about the disease entity is that it's invisible. At least on the scale I plan to simulate, the virus is microscopic and therefore never rendered. Just like in the real world, we never see viruses moving through the air because they're much too small for us to perceive with the naked eye. Even so, ECS places no constraints on whether entities are visible, so it's as much its own entity as the environment or any other visible entity in the simulation. Last but not least, we need to populate our environment with agents. These agents represent creatures that can contract and transmit diseases as they move around the environment. But once again, with ECS, we can define whatever properties we think might add sophistication and realism. Obviously, we create a unique entity for each agent or creature we wish to represent, and like before, we're free to add relevant and personalized characteristics. We can add a genes component that defines an agent's viral resistance or immunity to a given disease. A personality component could specify how close an agent is willing to get to others, and whether that agent is cognizant of the boundaries preferred by other agents. An apparel component could include various forms of clothing or personal protective equipment like masks and gloves that might impact disease transmission, etc. Once we've set up our entities and their comprising components, we'll also need to add the systems that define the interactions between them. Given our main objectives, some of these systems are rather obvious. We might create a motion system that allows agents to move about the map, a transmission system that enables the disease to spread from one agent to another depending on the disease profile, as well as agent positions and immunities, and a weather system that specifies the environment temperature depending on the time of day. However, we can also start modifying or defining systems to incorporate more complex or less obvious dynamics to the simulation. We could modify the motion system such that, depending on an agent's awareness, maybe it tends to move away from other agents that are sick. We could adjust the transmission system to depend on the environment's temperature, such that it's less likely to spread when the temperature rises. We could also add an immune system, pun intended, that causes an agent's immunity to spike once it's infected, then slowly drop off over time after it recovers, and so on. With these entities, components, and systems in place, we can dial up or down any of the real-type properties, switch on or off any of the Boolean-type properties, and even dynamically add or remove components altogether. ECS enables us to modify nearly any aspect of the game world, including the entities and the mechanics of the game itself, leading to all kinds of potential starting conditions and simulation constraints. That'll allow us to do some really interesting comparisons of how different components and component attribute values influence the spread of the disease and its impact on the population. In addition to what I've described here, there are several other ways I hope to add complexity and realism to the simulation, but you'll have to tune in to future devlogs or simulation videos to see those ideas unfold. As promised, here's a preliminary sketch of how I'd like the heads-up display to look eventually. It's pretty simple and basic, but I anticipate adding a lot of additional sophistication as time progresses. The most important and obvious feature is the viewport in the bottom left through which you can see the 3D game world. The menu bar in the top left will provide file handling and configuration functionality. The two thin panels directly below will provide information and various details regarding the simulation. The clock in the top right will allow reversing, pausing, and fast-forwarding time. The toolbox on the right will provide various means to modify the game world or game state, for example by adding new agents, and the plot in the bottom right will show pertinent time-dependent behavior. There will be a lot of work that goes into each one of these pieces, so it might take quite some time before I'm able to reach this point. Nonetheless, with an interface like this, it's exciting to think how easy it'd be to create and run new simulations. Hopefully, in the future, you'll see this interface built out and the beginnings of a working simulator. I think you'll agree. If I can actually set aside time to build it, Affliction has the potential to be incredibly exciting and rewarding. I've furiously written down all kinds of ideas to explore in this application, including entities, components, and systems, user interface features, data analysis techniques, and so forth. If you've got an idea, leave a comment in the chat. Who knows, maybe it'll impact some of my design decisions. For now, however, I need to get started with the fundamentals, importing the Tartarus library and building up the basic set of entities that define the simulator's user interface. Subscribe if you want to stay up to date, and leave a thumbs up if you like this content. I hope you join me on this new journey. It'll be an exciting one. Until next time, remember that we often judge ourselves by our intentions and judge others by the consequences of their actions. When others fall short of our expectations, let's strive to show them the same patience and gentleness we hope to receive in our less honorable moments.